Well, good day to you, my dear friends. It's time to solve some LeetCode problems. Yeah. Again, the weather is very loud. The wind is very loud. So excuse me if it is too loud. Maybe only I can hear it. Maybe not. We'll see. But we have to solve some LeetCode problems no matter what. And let's start with a problem that we solved a few days ago, or maybe it was last week. And this one. First unique character in a string. Well, initially I did it in a very strange way. Initially. What is a problem? We have a string and we want to return an index of the first unique character in a string, like index of L in this word. I mean, T is also unique, but we want to return the earliest index, the first index, the index of the first unique character. And I did it in a very crazy manner. I don't even understand. Now let me think about it. What did I do here? Well, yes. I created a hash. Like, let's take this LeetCode. LeetCode. And I created a hash. I iterated, of course. And when I encountered L, I added to our hash L key with a value of 0, 0. Okay. Now E, I mean it's just an index, but 2 times. Then it's E, we add E. We don't have it in our hash yet, so we create the same thing, 1, 1. But now we have E again. We already have it, so we rewrite this second index with a new index. It becomes 2. And we continue more and more and more and more. Then we go through all our hash values. For example, we have a T here, and T is gonna be equal to what? let's see, it's gonna be 3 3, I think, and C is gonna be 4 4, and we iterate through values of this hash, all values, and we check only values where both indices are equal to each other. So we do not consider cases like that, because when they are not equal, it means that we encounter this letter more than once. So we only consider cases like this, and in cases like this, when we encounter one of these, we replace our min index value with the new value 0 or 3 or 4 if it is smaller than the current value, and we start with infinity. So if we have C, our minimum index is 4, then we encounter T and it becomes 3, and when we encounter L it becomes 1. But if we encounter something with 5, it doesn't replace our minimum value because it's bigger. That was my initial solution, and it's incredibly stupid. When I looked at this problem today, immediately I came up with a better approach. So first of all, let's count all the occurrences as characters tally. Now we iterate again. And of course we want to do this with index. And if hash letter is equal to 1, we're gonna immediately return index. That's it. And if we do not have such unique letters, then we want to return -1. And that's it. Maybe we do not want to turn our string to an array of characters twice. We can do this just once, of course. If we create something like special variable for this, right? Or we can just say for I in from 0 to s length -1 do the same. But what is letter in our case? We don't have a letter, so it's gonna be s I. Oh, that was long. I don't know why. Nice. So yeah, that's how we solve it. we create a hash of frequencies, you know, how frequent are these letters. So in LeetCode, L is gonna have 0 and E is gonna have, what is 0? Moron. 1, and E is gonna be 2, because in LeetCode we have E, not 2, even 3. Small e and T1s and so on. Blah blah blah. And then we iterate again. Iterate with index. So we take the first index, index 0, and it's a letter L. This is our key. We look in hash for L. It is equal to 1. Now this is true. And if it's true, then we return index. Return index. I mean, we encounter this letter immediately, and we immediately return the result because we want to return the earliest index. Nice. Now let's solve a problem from the first page. I got tired of repeating the rules of how I solve LeetCode problems every day. I hope by this point you already know my system. I'm not tired, okay. We just set the difficulty to easy and we sort by acceptance. That way we get like the easiest problems because they were approached and solved by the highest number of people. And today we're gonna solve, well, not solve, discuss, because it was solved some time ago. 2160. This one. The page is almost done. Oh, it's loud. Let me clean this up. So now we have a number, and this number, it consists of 4 digits, exactly 4 digits, and we want to split this number into 2 new numbers, and we want to use all the digits from the original number. The question is, what is the smallest, and we combine these 2 numbers, and we want to determine the minimum possible sum of these 2 numbers. And initially I had a very stupid solution. An hour ago I came up with a better one. So I examined every possible scenario. It's painful to watch, Jesus H. Christ. But today I looked at this problem and immediately I came up with a lot better solution. Because let's say we have 2932. 2932. Let's sort them. It's gonna be 2, 2, 3, 9. So what are 2 smallest 2-digit numbers that we can create? Well, we need to take the smallest number, the smallest digit, it's 2, and we need to take the second smallest number, put it here, then we take the third one, we put it here, and the last one, the biggest number, is here, because we want to have the smallest numbers at the decimal places, and the biggest numbers we want as ones, so that they are less dangerous that way. I mean, it's 9 or it's 90. Of course, it's better to have 9 if you want to create a small sum, smallest possible sum. So this is the approach we're gonna use. We sort them. Let's say sorted is num, but remember that this is a number. We want to make a digits out of it, and we want to sort these digits. And now what do we want to do? We want to take the first number, the smallest one, and we want to multiply it by 10, because it's not 2 plus 3, it's 20 plus 3, right? And it's 20 plus 9. We add to this sorted 2, and we have our first number. Then we add, well, pretty much the same thing, but it's 1 and 3, and that's our answer. And of course it can be done with, we can convert it to a string, and then we can use characters. Then we're gonna add them as strings, so we do not have to multiply, but in the end we want to convert them back to integer. Let's try this. I never know if I'm right. Oh yeah. I make this mistake all the time. I don't know what's wrong with me. And this is of course correct, but you know what is my problem with that approach? Yeah, our intuition was correct, that we should sort numbers and then create two numbers each consisting of 2 digits. But how do we know that this is the smallest possible sum and it's not like 1 digit number plus some 3 digit numbers? Why do we decide to split like that, you know? How do we know that our intuition is correct, aside from the fact that our test cases were passed? How do we know? And let's look at the solutions. They are all similar to this. It's so slow today. No, this one is a strange one. I will give you that. But still, they are pretty much the same. But no one explains why. Why should we split like that? And let's try to think about this problem. So we have 4 numbers, like A, when they are sorted, B, C, and D, right? And when we create numbers splitting like this, what's it gonna be? A is the smallest, so it's A multiplied by 10 plus B, not plus B, plus C plus B multiplied by 10 plus D, right? And if we want to split the same thing 2, 2, 3 and 9 into one digit number and 3-digit number, then for our 1-digit number we want the biggest digit, like 9, and here we want 2, 2, 3, right? So this approach is going to give us D plus A multiplied by 100 plus B multiplied by 10 plus C. No. A is the smallest. Yes, A, B, C, of course, because the smaller is the number, the further left we want to move it in our 3-digit number, so that the biggest digit is gonna be into ones. It's hard to explain. So we have these two formulas, let's call it, and we have C in both, so C doesn't affect anything. We can remove it from both expressions, and D doesn't matter, and B10 doesn't matter, so only A matters, and 10A is definitely smaller than 100 A's. Well, in our case at least, because we have a positive digits. And you know, if we may say, why do we use D here and C here? Maybe we want to use C here and D here, but it doesn't change anything. Still they're gonna annihilate each other. Or why do we use, wait a second, A and B like that? Maybe it's A10 and B100. But then A10 destroy each other, and B10 is definitely smaller than B100. So either way, it doesn't matter. This one is smaller than that one, and I am not sure if this is a solid enough proof, but that's my proof. And now let's solve something new. Do you remember some time ago we started solving problems from one of the cards about arrays? We have many more problems here. They're usually not easy. Well, they're not hard, but they have some additional constraints, like let's do everything in place. Hate it. So what is the problem here? Sort array by parity. Given an integer array nums, move all the even integers at the beginning of the array followed by all the odd integers. Return any array that satisfies this condition. Well, luckily for us, they do not ask to do this in place Oh, and I already solved this problem some time ago. Have we discussed it? I don't remember. Accepted. Let me check something. Sort array by parity. It was solved a long time ago. Before I started streaming, so we can discuss it, you know. Let's resolve this problem. And you know, I solved it in an ugly way. Oh, it's ugly. Ah, I was so stupid back in the day. So I solved this problem just by always adding odd numbers to the end of the array and like sticking even numbers in the beginning, and it's very bad. Luckily, this constraint is generous. And what would be a better approach here? Well, obviously we can create two arrays, evens and odds. And if it's even, we add to evens. If it's odd, we add to odds against all odds, and then we just merge. You can even do something like concat to modify evens. And also we can call it just result. Oops. Like this. So this is a solution. Or we can iterate twice. I think it's better to do something like this. What else do we have here? Oh, such a strange order. Replace elements with greater element on right side. So given an array R, replace every element in that array with the greatest element among the elements to the right. Okay. And replace the last element with -1. Let's start from the end. Oh, and it's also solved. Did I start from the end? Yes, I started from the end. I want to solve something new. When was it solved? Long time ago. So what is... Oh, this is something strange. Oh no, it's not strange. Let's say we have this. I'm copying it like I can paste it here. Can I? Well, I can. That's funny. Whoa! Science bitch. That's cool. So we start here. We take we take this value 1. So our max element is 1 now because we do not have anything else. So our max is equal to 1. We replace the element itself with -1 because this is our condition. Replace the last element with -1. Well, because it doesn't have anything to the right. And then we move here. Take this number 6 and we check what's bigger, this new number or our previous max value. And of course new number is bigger, so our max is now equal to 6. But before that we need some extra variable to store this 6 somewhere, because we just not 6, we want to store this previous max, well, or 6, you know, it doesn't matter. Let's call it old value. Old value is 6. Then we replace 6 with max. No, max was 1 at this point, so it becomes 1. And for max we check what is bigger, 6 or not 6. How do we know that it is 6? Old value or previous max. That's what we check. We do that again and again and again. So we know we have 6 as a max. We set old value to 4. We replace 4 with 6. We check what's bigger, 6 or 4, and we get 6. 6 is still the biggest we encountered. We go here, I keep 5 in memory. It's gonna be 6, because it's the biggest one we encountered to the right. But now we check what is bigger, 5 or 6. It's still 6. We go here, same story, it's gonna be 6. But what is bigger, 18 or 6? Well, 18 is bigger. Our new max is 18. We go here, we replace 17 with 18, and we are done. 18, 6, 6, 6, 1 minus 1. Yep. So this is what we do here. Of course, I found a way to overcomplicate things, but that's me, you know. So let's do the same, and while I is bigger than 0, like this, and we're gonna decrease our I every step. So we already replaced this one. So we want to start not with let's start at -2. This one is already fixed. So odd value, we called it. Yeah. So old value is Ri. New Ri is max, and max is max or odd value max. Something like this. Pum, 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 pum. Oh. Oh, that's funny. That's a funny condition. We start with I smaller than 0. Okay, so I is 2. We're gonna increase our I, of course. We want to use minus here. That's gonna be better. Our condition is while we have no not good. Yep. Oops. Yeah, that's right. But I really want to solve something new. Come on. What about this one? Remove duplicates. Oh, come on. What about move zeros? Beautiful. Kids from sorted away. Looks familiar. Maybe we encountered this problem here. Nope. Ah, it's very familiar. When did we solve this one? What? A minute ago. Yeah, it's recent. We already discussed this problem. Let me quickly check. I'm not sure. I'll check later. It looks like we solved it. Now, move zeros. Okay. Given an integer array nums, move all zeros to the end of it while maintaining the relative order of the non-zero elements. Note that you must do this in place without making a copy of the array. Maybe we do not even need this pointer. So if num is equal to 0, we increase our offset by 1. I'm gonna do something funny here. Nope. Like this. Oh, that's ugly for sure. Great. Let's okay. That's funny. I mean, it's too many replacements. Okay, we can do that only if offset is bigger than 0. Otherwise it doesn't make much sense, but we can also leave it like this. So let's say we have an array, this one. Let's go here. Boom. Oh no. Come on. We have an offset variable. We can do this. Okay. 0. And we iterate. If we have a 0, we increase our offset. Now it's 1. And immediately we go forward. If it doesn't equal 0, what do we do? Well, we replace the element itself with a 0, and we replace the element with the same index, which is 1. Not with the same index, we take this index 1 and we take element, this index minus offset. In our case, this is 0, no, this is 1 already, because we already encountered 1, 0. So we have 0. We replace this with 1. We go here, another 0. Our offset is 2. We go here, it's 3. Well, what do we do? Well, we replace 3 with 0. This is also 0. And 0, 1, 2, 3. An index is 3 here. So it's 3 minus offset, which is 2, is going to be equal 1. This one, we replace this 0 with 3. We continue moving forward. This is not 0, so offset is 3. We replace this with 0. We replace this 0 with 1. Here 2, it's not 0. It's gonna be 0 now. And we replace this with 2. 1, 3, 1, 2, 0, 0. Oh, and I lied to you about this. And before I introduced this condition, well, let's say we have something like 1, 2, 3. We do not have any zeros here, so our offset is 0. And what did we do when we didn't have this check? We replaced 1 with 0, and then we immediately replaced with 0 with 1 back. But you know, it's an unnecessary operation. We can just make this check. Like maybe next if no. Oh, I'm stupid. It was 12. It wasn't 1 and 2, but it doesn't matter. It doesn't really matter. It works. And what do we have in this roadmap? Some medium problem. Don't know. Tomorrow. And these problems, they are all easy, right? I guess so. No zeros. Oh, we can't see. Yeah, of course it's an easy problem. So all of them are easy probably. Okay, let's look into this. The problem is when I solve too many problems in one stream, when I upload it to YouTube, I have a constant problem because in my title for a YouTube video I list all solved problems by their numbers, but there is a limit for the length of the title. It can be no bigger than 100 characters. And when I solve too many problems, well, I can't list them all. But okay. So, given an array of strings stars, group the anagrams together. You can return the answer in any order. What? Whoa. So we have, we're gonna need a hash for this. Can't do anything these days without a hash. No. So if you want to sort it, of course. Now in our hash as the values we have the strings. As a key we have the same string. Well sorted. Right, and we want to return just hash values. We can't sort strings, right? Yeah, for sure. Can we have an array as a key for hash? I don't even remember. Yeah, we can. Of course, why not? We can have anything as a key. Something happened. Well, thank you very much. Appreciate it a lot. Well, that was an easy problem. Still I'm thinking, what if we join? Is it better than having array as a... Because when we... When you look for a key and it's an array, we have to compare arrays. But it's probably the same as comparing strings. Doesn't matter at all. So yeah, let's not join anything. This is our final solution. It's done. I just don't like our milliseconds here. But that's it. So we solved a lot today. And of course we're gonna continue tomorrow. Solved. And tomorrow I'm tired. Tomorrow I'll give you the best approaches for these problems. Now we just solved them. Yesterday we're gonna discuss the best approaches that I can find or invent. So I'll see you tomorrow. Thank you very much for being here. Oh, someone wrote something. Wait a second. Okay, what's up? No, again, every day. This happens every day. No, I don't need any custom graphics, I'm sorry. I hoped you were a Ruby enthusiast, but no such luck. They do not exist. I am a dying breed, I guess. Well, oh, zombie killer whale. Almost missed you somehow. I missed the whale. I'm sorry, man. Sometimes I just forgot to look because I do not have that many messages, so I do not check this chat. But yes, it was easy. I think previous problems about zeros, easy problem, was harder than this medium problem. But it's done. That's it for today. Thank you, thank you. Oh, we have some drops. I hope it was watchable. Well, I'll see you tomorrow. Goodbye, goodbye. See you later, my dear whale.